Welcome to the lecture series of signals and systems. In the previous lecture, we have seen some important properties of the Laplace transform, including time shift property and time reversal property also. And in this lecture, we will discuss some more important property regarding this tool, Laplace transform. So, the property is transform of derivatives. Transform of means if we are going to transform, what will happen if we are going to transform the derivative of the signal xt. So suppose there is a signal xt which Laplace transform is known, which is x of s. Then what will be the Laplace transform of derivative of xt, and it will be equal to s times x of s minus s minus x of g. Means if we will differentiate the signal in the time domain, we will get the Laplace transform as given here. We can discuss the proof as we know that the Laplace transform of a given signal xt can be determined by using the relation t is from minus infinite to infinite x of t e power minus st dt. Or if xt is a causal signal, then this can be written as limit from 0 to infinite xt e power minus st dt. If xt is a causal signal, but what we have to get is we have to get the Laplace transform of the derivative of xt. Means we have to get the Laplace transform of d by dt of xt. It means that this will become integration from 0 to infinite d by dt of xt into e power minus st dt. In place of xt, I will put d by dt of xt here. Now we can determine the value of this integration by using the integration by parts technique. So I will consider this e power minus st as first function and this is the second function, and the formula to get the integration by part is if there are two functions first and second, then we can determine the integration as first function integration of second function minus integration of differentiation of first function integration of second function and integration of whole. So by using this formula, we can determine the value of the given integration. We can determine this value of this integration by using this relation. So here first I will write function 1 means e power minus st integration is from 0 to infinite first function integration of second function means integration of d by dt of xt minus integration of differentiation of first function means d by dt of e power minus st integration of d by dt of xt dt, integration of this whole with respect to t. So here it is first function, integration of second function, limit will be from 0 to infinite. Here also the limit will be from 0 to infinite. So first function integration of second function minus integration of differentiation of first function integration of second function. Now integration of differentiation, because we are differentiating xt with respect to t, and also same time we are integrating the same signal xt with respect to t. So integration and differentiation will get cancelled and this will become equal to e power minus st, e power minus st xt, limit is from 0 to infinite, minus, now this will become e power minus st, this will become minus s into e power minus st, minus s into e power minus st, and its differentiation and integration will become xt, and this is the integration of whole, limit is from 0 to infinite. Again differentiation of e power minus st will become minus s times e power minus st minus s times e power minus st, and integration and differentiation of xt will become xt. So I will put xt as it is. Now this can be further simplified as e power minus st xt, where limit is from 0 to infinite, minus 1 minus is already there and it is minus s, I will write it as plus. Now this will become minus, this will become s times integration from 0 to infinite xt e power minus st dt. This will become integration of xt into e power minus st dt. So I will write it as, when I will put t equal to infinite here, this will become 0. So this is 0 minus, when I will write 0 here, this will become 1 and this will become x of 0 plus s times, and what is this? This is the relation to get the Laplace transform of the signal xt. So this will become s times x of s. It implies that I can write the Laplace transform of d by dt of xt as s times x of s minus x of 0. This is what we will get if I will differentiate the given signal in the time domain. If I will differentiate the given signal in the time domain, we will get the difference of these two. And if the signal will be differentiated one more times, means what will be the Laplace transform of d2 by dt square xt. What is the Laplace transform of d2 x of t by dt square? This will be equal to, when this signal is differentiated only once, I will get only s here, s power 1, and if it is differentiated 2 times, this will become s square of xs minus s times x of 0 minus, now this will become s power 0 x dash 0. Similarly, if the signal is differentiated n times, d power n x of t by dt power n, then this will be equal to s power n x of s minus s power n minus 1 x of 0 minus s power n minus 2 x dash of 0 minus s power n minus 3 x double dash 0 minus dash dash dash, the last term will be, this will become s power n minus n, means s power 0 x power x differentiation of x n minus 1 times 0. This is what we will get if I will differentiate the signal xt n times. Then this will become s power n x of s minus s power n minus 1 x of 0 minus s power n minus 2 x dash 0 minus s power n minus 3 x double dash 0, and here it is, if it is not visible, this will be equal to minus s power n minus n, means s power 0 I will write it as 1 x differentiation of x n minus 1 times 0. This is what we will get after the differentiation. So this is the transformation or differentiation property of the Laplace transform. Now what will happen if we integrate the signal in the time domain? Means we have to get the Laplace transform of the signal xt when it is integrated. Suppose the given signal is minus infinite to d x tau beta, and we have to get the Laplace transform of this signal, where Laplace transform of xt is known. This is equal to capital X of s. Laplace transform of xt is equal to x of s. Then from here, what will be the value of f of 0? This will be equal to, from, I will write 0 in place of t. So this will be equal to minus infinite to 0 x of tau b. Now we have to get the Laplace transform of this given signal f of t. So the Laplace transform of this signal f of t will be equal to Laplace transform of, first of all I will differentiate the signal xt, this ft, to get the signal xt back. So after differentiation, d by dt of ft will be equal to signal x of t, d by dt of xt, because integration and differentiation will cancel each other, and after differentiating the signal ft, we will get the signal back x of t. Now find the Laplace transform of this given signal d by dt of ft, which is equal to x of s, which is equal to x of s. Now this will become, because Laplace transform of xt will be equal to x of s, and we have to get the Laplace transform, means we have to get this signal f of s. We have to get this signal f of x, because ft is the integration of signal x tau d tau. Now this will become from the previous example, from the previous property, Laplace transform of derivative will become s times f of s minus small f of 0 is equal to capital X of s. Now, because we have to get the value of this f of s, from here this will become equal to f of s become equal to x of 1 upon s times x of s plus f of 0. From here, when it will be transferred to the right side of the equation, this will become x of s plus f of 0, and to get the f of s, I will divide both sides with s. Now this will become f of s is equal to 1 by s times x of s plus f of 0, and from here we will get the value of f of 0 as it is integration from minus infinite to 0 x of tau d tau. So now I will put the value of f of 0 here. This will become f of s is equal to x of s divided by s plus 1 by s. Value of f of 0 is from, it is minus infinite to 0, minus infinite to 0 x of tau 0. This is the transform of integration property in the Laplace transform. So we have seen both the properties. First one is d by dt of xt will be transformed as s times x of s minus x of 0, and integration of xt dt will be transformed as xs upon s plus 1 upon s times integration from minus infinite to 0 x tau d tau. This is the property of differentiation and property of integration in the Laplace transform. Now come to the next property, which is frequency shift property of the Laplace transform, or we can say that it is shifting in S domain. The next property is shifting in S domain. Shifting in S domain. Suppose there is a signal xt and Laplace transform of this signal xt is x of s, and we have to get the Laplace transform of this given signal e power at x of t. We have to get the Laplace transform of this signal. Now we know that the Laplace transform of signal x of t is equal to integration from 0 to infinite. If it is a causal signal, then I will put limit here from 0 to infinite. So this will become limit from 0 to infinite x of t e power minus st d. And we have to get the Laplace by using this relation. We have to get the Laplace transform of e power minus at x of t. So Laplace transform of e power at or minus at, I will define both the properties when it is multiplied by e power minus at and when it is multiplied by e power plus at. This will become equal to 0 to infinite, in place of xt, now I will put e power 80 xt. So this will become e power 80 x of t e power minus st dt. Now combine both these terms, e power plus 80 into e power minus 80. Combine both these two, e power plus 80 into e power minus st. So this will become Laplace transform of xt multiplied by e power 80 will be equal to limit from 0 to infinite e power xt into e power minus s minus a into t. So from here we can compare with the standard relation that we know that x of s means Laplace transform of xt can be written as 0 to infinite xt e power minus st dt. But in place of s here, in place of s, it is written s minus a. This means that this is the value of the signal x of s minus a. This is the value of the signal x of s minus a. It means that if the Laplace transform of a given signal xt is equal to x of s, then the Laplace transform of the signal xt multiplied by a power 80 will be equal to x of s minus a. Meaning that if we multiply the signal in the time domain with the exponential e power 80, then the signal in the frequency domain, or we can say that signal in the s domain, will be shifted right by a unit. Also, if we multiply the signal xt, means if we multiply the signal in the time domain with e power minus 80, then in the s domain the signal will be shifted left by a unit. It means that this will become x of s plus a. This is again an important property of the Laplace transform, which is called shifting in x domain, because if we are multiplying an exponential in the time domain, the signal in the s domain will be shifted either right by a, or it will be shifted either left by a, depending upon whether it is multiplied by e power minus 80 or it is multiplied by e power plus 80. So this is called frequency shift property of the Laplace transform. Now come to the next, which is differentiation in S domain. Earlier we have seen the property differentiation in time domain. Now we will see another property, differentiation in S domain. Differentiation in S domain. Earlier we have seen if signal xt has the Laplace transform x of s and it is differentiated in time domain, then this will result in a transform of s times x of s minus x of 0. S times x of s minus x of 0. Now the given property states that if the signal differentiated in S domain, means if signal x of s differentiated with respect to s, it means that the signal xt will be multiplied by variable t with negative sign. This is the time differentiation property of the Laplace transform, and this is the differentiation in S domain property of the Laplace transform. We can find the proof also. We know that the Laplace transform of signal xt, which is equal to x of s, can be determined by using this relation, limit from, I will put it as from 0 to infinite x of t e power minus st. Now differentiate both sides of this relation with respect to s. Differentiating both sides with respect to s, we will get d by ds of x of s will be equal to, because with respect to xt, with respect to s, this signal xt is a constant. With respect to s, xt is a constant, so it will be outside of the differentiation. We will differentiate only this term e power minus st. So this will become integration from 0 to infinite x of t d by ds of e power minus st dt. And this can be further written as integration from 0 to infinite xt and differentiation of e power minus st with respect to x will be equal to e t minus t times e power minus st, minus t times e power minus st, because t is a constant with respect to s dt. Or it can be further written as integration from 0 to infinite t times xt e power minus st dt. Or we can write it as Laplace transform of t times xt. This is equal to Laplace transform of t times x of t, because in place of xt it is written here t times x of t. It means that this is the Laplace transform of t x of t. Now also one minus sign is here, which is equal to minus, so I will write here minus, I will write here Laplace transform of minus t times x of t, or we can simply put this sign to the left side of this differentiation. This is equal to minus t times x of s upon ds. It means that the property states that if we differentiate the signal in the s domain, then the signal in the time domain will be multiplied by a variable minus t. Or we can generalize this formula as if we differentiate the signal in the s domain n times. If we will differentiate the signal in the s domain n times, then the signal in the time domain will be multiplied by t power n, and in place of minus sign I will put minus 1 power n here, because we are going to differentiate the signal n times. This is the general formula to represent the differentiation in S domain property of the Laplace transform. Now some more properties are there which are important, like convolution and multiplication property of the Laplace transform. The next is convolution property. This convolution property of the Laplace transform states that if the Laplace transform of x1t is x1s and Laplace transform of x2t is x2s, then the Laplace transform of x1t convolution with x2t will be equal to x1 of s into x2 of s. Very important property to get the response of a system. If the impulse response of the system is known, we have to convert the input with the impulse response of the system, and for that purpose this is a powerful tool. Instead of getting the convolution of two signals x1t and x2t, we will multiply these signals in the s domain, and then we will get the inverse Laplace transform of this signal x1s into x2s. So for the proof, we know that the Laplace transform of x1t convolution with x2t will be equal to integration from 0 to infinite. I will consider these signals x1t and x2t as causal signals. So this will be equal to x1t convolution with x2t into e power minus st, and we know that convolution of two signals x1t and x2t can be written as integration from minus infinite to t x1 t minus tau into x2 tau d tau, or it can also be written as minus infinite to t x1 tau x2 t minus tau d. So I will put any of these relations in place of x1t convolution with x2t in this equation. So this will become Laplace transform of x1t convolution with x2t will be equal to integration from 0 to infinite. In place of this, I will put x1 t minus tau x2 tau d tau integration from 0 to t and whole integration e power minus st dt. This is the value of x1t convolution with x2t. Now, after changing the order of integration, changing the After changing the order of integration, the Laplace transform of x1t convolution with x2t will be equal to integration from 0 to infinite x2 tau integration in place of t I will put here 0 to infinite x1 t minus tau d tau into e power minus st dt, or we can put consider t minus tau as another variable. Suppose this is equal to z, then if the limit on the t is equal to 0, suppose when t will be equal to 0, this will be equal to minus tau, and when t will be equal to infinite, the z will be equal to infinite. Now from here we can write t is equal to z plus tau. We can write as t is equal to z plus tau. Now this will become integration from 0 to infinite x2 tau into integration in place of t minus tau I will put z x1 z e power minus s, and in place of t I will put z plus tau and d tau, and in place of dt now this will become dz. Again this will be equal to 0 to infinite x2 tau d tau, I will put d tau here, and this will become integration from 0 to infinite x1 z e power minus s into z into e power minus s into tau dz. I will rearrange this e power minus s tau. I will put this e power minus s tau with x2 of tau. I will put this e power minus s tau with x2 of tau, and now this will be equal to x2 of tau e power minus s tau, x2 of tau e power minus s tau d tau into integration from 0 to infinite x1 z e power minus sz dz. This is integration from 0 to infinite x2 tau e power minus s tau d tau into limit from 0 to infinite x1 z e power minus sz dz. This is what? This is the Laplace transform of the signal x2t, and this is the Laplace transform of signal x1t, means this is x1 of s and this is x2 of s. It means that we can write that the Laplace transform of the convolution of x1t with x2t, convolution of x1t with x2t will be equal to Laplace transform of x1, which is equal to x1 of s, into Laplace transform of the signal x2t, which is equal to x2 of s. So this is an important tool to get the response of an LTI system, because if the impulse response of the LTI system is known, suppose impulse response of this LTI system is h of t, and the input given here is x of t. Then output of this system will be equal to x of t convolution with h of t. If the impulse response ht of the system is known. So in that case, to get the convolution of these two signals xt and ht, instead of getting the because convolution is far more complex than getting the Laplace transform. So instead of getting the convolution of these two signals, we will get the multiplication of their Laplace transform. Suppose the Laplace transform of xt is x of s and Laplace transform of xt is capital H of s. Then the Laplace transform of x1 Laplace transform of xt convolution with ht will be equal to x of s into h of s. And to get the signal xt convolution with ht back, we will get the inverse Laplace transform of these signals. Inverse Laplace transform of xs into hs, and we will get the signal convolution of the signal in the time domain. So that's why the convolution property of the Laplace transform is important. So this is all for this lecture. There are some more properties like multiplication of the signal, conjugation, and Parseval's theorem, and final and initial value theorems. So in the coming lecture, we will discuss these remaining properties. This is all for this lecture. Thank you.